Okay, so far in the world of statistical inference, we've used the confidence interval as our only tool. And with the confidence interval, we're kind of flying blind, so to speak. We're looking for an estimate for a value. And so far, we just work with proportions or means. The hypothesis test is a little bit cleaner form of inference, but it requires a hypothesis. It requires a claim is being made. So to explore the concept to begin with, we have to pick something that will look at either a mean or a proportion. In this case, we're going to be talking about proportions, right? And we're going to use a statistical applet that goes along with your textbook website. So if you go to, this is where our online quizzes are, our practice of statistics website. The quickest way, I assigned chapter 9 in here, but I don't know if the applet comes up all the time automatically. So if you click on resources over here, the star to the left, and look for resources or content by type, looks like it still has me in the place where I was before. So under resources, you might need to click on content by type first, and then select statistical applets. We've used several already. The confidence intervals, the correlation, and regression were pretty useful in exploring those topics. But you're going to choose this one, the statistical applets, the reasoning of a hypothesis test or reasoning of a significance test. And it looks like this. Okay? So we have the worksheet that goes along with it that I'm going to walk you through. Okay? So what we have in this applet is a college basketball coach who claims that his players make 80% of their free throws. That's the claim, right? So in the language of confidence intervals and parameters, right, we would be claiming that P equals 0.8. And what is P? It's the true proportion of free throws that any of his players make, okay? So that's what we're talking about here. So we're going to choose different players, but the one player is what we are testing. We're testing each player at, individually, and we're looking to see, is that claim true about this particular player? Does he make 80% of his free throws or not? So, just thinking about this, if a player comes up and shoots 10 shots and only makes 5 of them, would you decide at that moment that that player is not really an 80% free throw shooter? We know the law of large numbers tells us that the 80% is what needs to be true in the long run. If we only have him shoot 10 shots, might not be enough. So one of the things we usually do with this when we work on this in groups is how many shots do you think we should have this player make in order to make a conclusion? And there is a right or wrong answer here, right? So as we think about that, we're testing a proportion, right? We are going to base our decision on whether that proportion is true based on a sampling distribution that we believe is normal, okay? So if this player is going to shoot a certain number of shots, we believe the true proportion of shots he makes is 80%. We know that means sometimes he might shoot a little over 80%. He won't always make 80% of whatever sample size of shots we give him. But what we want to do is figure out how far away would we want P hat to live so that we would believe that this is no longer true, that we would say the 0.8 doesn't seem to be true. So we have to go with the assumption that these P hats are normally distributed, which means we need n times P to be greater than or equal to 10, and we need n times 1 minus P to be greater than or equal to 10. And the nice thing about this, which we didn't have with confidence intervals, is we have a claim value of P. So we ought to be able to figure out, and the 0.8 is not going to be a problem. If we had him shoot, probably a dozen shots, 80% of that might get us past 10. But it's the 0.2 that's going to be a problem, right? I need this value of n times 0.2 to be greater than or equal to 10. If n times 0.2 is greater than or equal to 10, then n times 0.8 certainly would be. So let's think about that. N times 0.8, in order for that to equal 10, we would just divide both sides of this by 0.8, right? We need to figure out what's 10, 80, or 0.2 rather. Let's fix that. We know the 0.8 is going to be satisfied if 0.2 is satisfied. So we would take 10 and divide by 0.2. So what we're going to need is for n to be 50, right? Think about it. If he shoots 50 shots, and he makes exactly 40, that's exactly 80%, but he might make 41 or 42 or 43, or he might make 39 or 38 or 37. So now all those p hats will be normally distributed around 0.8. Otherwise, the distribution would be skewed to the left, right? We would have, if we only shot 10 shots, 8 out of 10 would be most likely, and then we'd have a skew to the left situation. But if we shoot 50 shots, so that is the correct answer, we need him to shoot 50 so that we can assume this normal sampling distribution that we're going to base our inferential conclusion on. So I'm going to go through the applet one time and I'll answer these questions, and then you'll have a chance to do it on your own as well after you've completed the Edpuzzle. There's a Quiz Me button at the end so we can see how everybody did. Now the purpose of this is not to get an 80% free throw shooter, but to simply test the shooter that you had. And there's a couple layers to this app that I want to show you, which I think is interesting, to help us understand this concept of a hypothesis test and also some of the errors that could be made in it. And by error, I mean we make a decision. It's possible that our free throw shooter shoots 80% and we conclude that he doesn't based on our sample. This is possible. Okay, we're deciding that from the outset. And in fact, if we say we have to decide at some point what's this area going to be. If we say this is going to be 0.05, that's what we call our significance level. So from the beginning, before I ever run this test, there's a 5% chance that I will get a p-hat that will lead me to believe that 0.8 is not true and 0.8 actually is true. So I want to start thinking about what that means in context. That's what we mean by an error. But there's only 5 out of 100 times that might happen. If we make that area in the tail be 1%, it's much less likely that we would make that error. All right. Now, what we're also able to do here is peek behind the curtain. See this button that says Show True Probability? In reality, when we actually do research, we're not able to do that. All right. So I'm going to have my shooter shoot 50 shots. So I'm going to hit Shoot, and we get to watch the balls going in. This definitely looks like an 80% shooter. He's making a lot more than he's missing. And you can see that how the graphic works out. It really gives you that law of large numbers look to it, right? And now as the numbers get larger, right? At first I thought he looked like an 80% shooter, but now he looks like he's a little bit below 80%. And now maybe he's getting back up closer to 80%. Okay. All right, and we'll use this as our data. So I'm going to come back to the worksheet here, and how many did my shooter made 35 shots, which is 70%. Okay, 30, that said how many? So let's answer the question correctly. 35. So what would that p-hat be? It would be 35 out of 50, right? That's the difference between a count and a proportion. So he made 70%. Do I think he's a 80% shooter? Why or why not? This is your opinion. I'm going to say no, and I'm going to say I think, and this is just my opinion, that 35 out of 50 is too few for an 80% shooter. And remember, there's a chance that I'm wrong, right? Maybe he really is an 80% shooter, and we want to talk about what that error means. If I'm wrong, that's one of our types of errors. We'll talk about that at the end of the activity. And if I'm right, it's a correct decision, okay? The other way we could be wrong is I could say, yes, I think, he made 35 out of 50. 70% of 50 is close enough to 80% that I'm going to believe his claim. I'm going to believe that he is an 80% shooter. So this is, this is not a right or wrong. This is an opinion, and I'm just expressing it as such, okay? So the concept of the hypothesis test works a lot like our criminal justice system, okay? We have the null hypothesis, and in our criminal justice system, the null hypothesis is that a defendant is innocent unless there's significant evidence to the contrary of that, and that's what we have laid out at the top here, okay? So we're going to believe that the coach's claim is true. We're going to believe that it's 80%. So even though I answered my opinion was just my opinion after watching him shoot 50 shots, right? Before he shoots any shots, we're believing that he makes 80%. After he shot 50 shots, I made a conclusion. But now we're going to not just listen to my opinion or your opinion about the significance of the 70%. We're going to use the central limit theorem. We're going to use what we know about probability theory to make a better decision, more accurate decision. And maybe that decision will agree with my opinion. Maybe it won't. Okay. So the alternate hypothesis. Now, I don't think the coach cares if he makes more than 80%. In fact, he says they all make at least 80%. So it would be okay if he makes more than 80%. If he makes less than 80%, then now we have a contradiction to that claim. Okay. Some textbooks you'll see they might put the null hypothesis like this. They might say for like a one-tailed test like this that it's greater than or equal to 0.8. I never do that. I think it's much easier just to say that the null, nothing, no difference, is just always an equal sign, and you'll always be okay with that. So if our sample statistic falls significantly, right, how do we measure that? Probability, right? And in this case, the central limit theorem and a normal sampling distribution. For the t-distribution, we will use, or for means, we'll use the t-distribution, same as we did for confidence intervals. Okay, so we have to decide ahead of time what we're going to consider unusual. If something happens less than 5% of the time, is that unusual? We will call that an alpha value of 5. And we're going to let alpha, that's our significance level, be 5%. This is the probability that we will incorrectly reject the null hypothesis, right? So the null hypothesis is that 0.8 lives in the middle here. Now I'm going to say ahead of time, I'm going to put this out here and put a 0.05 in this tail. And I'm going to say if he makes less than this many shots, or this proportion of shots, I'm going to conclude that he's less than an 80% shooter. So before we even start this test, before he even shoots a shot, there's a 5% chance that I would make that what we call a type 1 error, where I reject the null hypothesis, but it was actually true. In our criminal justice system, this is the most egregious error, right? This is where the defendant is actually innocent and the jury concludes that the defendant is guilty. And our justice system is designed to counter that, because we have that mantra of believing innocent until proven guilty. It doesn't go the other way around. Now, the other result of that, if we have a system that's designed that way, it means that it's more likely that a guilty person will be let free than an innocent person is convicted wrongfully. And I think most people would agree that is the right way to have the system designed. Certainly we want a place where we make the right decisions, where guilty people are found guilty and innocent people are always found innocent. But the more egregious of the two, I mean, nobody's going to be excited if a guilty person is found innocent, but it's much more egregious if an innocent person is found guilty. I think most would agree with that. So what's our standard deviation of this sampling distribution? It's 0.8, same as it was in the last chapter, and in fact in the last several chapters. 0.8, which is p, times 0.2, which is 1 minus p, divided by 50, and we take the square root of that. And that's probably more decimal places than I need. But this is how our sampling distribution is going to behave. So now on the curve above, I've already done this. Plot where your sample statistic p would fall in relation to the mean of the sampling distribution. So, our sample statistic p hat, right, was 0.7, would fall somewhere, if the standard deviations are about 5%, we're pretty close. 0.7 our p hat would fall somewhere here. It's down below it, right? Sketch the area representing the probability of getting this sample by chance. Okay, so let me just erase a little bit here. So let's go ahead and put p hat, looks like it would be a little bit less than 2 standard deviations below. 0.7 lives here. And the area, or the probability below that, we're going to call that the p-value. That's the probability that would happen by chance. What is that probability? This is a normal CDF situation. We've been doing this since September. So we go from normal CDF, like let's say -100. It's excessively far down below there. Or we could just say 0, right? These are all decimals. Probably don't need to be that excessive with the -100. Since we're dealing with proportions, we could just go from 0 to 0.7 with a mean of 8 and a standard deviation of 0.0567. Okay, so we said so the probability of that happening is 0.03855, and remember what we said was significant, 0.05. So I just found a test statistic that happens less than 5% of the time. So our conclusion in that situation would be to reject that null hypothesis of 0.8. We would decide, and we don't know if we're right or wrong, okay? If I'm right, it's a correct decision. If I'm wrong, this is what we call a type 1 error. But there's only a 5% chance of that type 1 error to begin with, okay? So I got a probability of 0.03855 of that test statistic. So based on this test and probability, I would make the same decision I made from my opinion in the beginning. I would conclude that he's not an 80% free throw shooter. I think that he makes less than 80% of his free throws based on that. So on the third page of the activity, we have our definition of the p-value. It's the probability of getting the statistic you got or one further from the null hypothesis value. After calculating the p-value, do you think the null hypothesis is true? I'm going to continue to say no, right, since it's less than 5%. Okay. And I did not make this mantra up on my own, but some of my college students many years ago mentioned this to me, that somebody taught them to memorize it this way. But if the p-value is low, the null must go. Good way to remember that. If you're trying to figure out, when I have this p-value, if it's really small, what do I do with the null hypothesis? If the p-value is low, the null must go. Nice little mnemonic device, so I like to tell my students about that. So now we're going to go back to the applet and see if we were right or wrong. Okay, so let's jump back to the applet, and in reality, we never have this luxury of being able to peek behind the curtain, but here we can. All right, so I'm going to click on Show True Probability, and lo and behold, we were right. This player actually makes only 60%, so we made a correct decision. Now, it's possible that he was an 80% shooter, and just out of these 50 shots, that something that happens less than 5% of the time happened to happen, but we happened to make a correct decision. In practice, we really don't know whether we made a correct decision or not. We happen to make a correct decision here. But when we do research or we make a decision based on a claim, we just have one sample, and we can't really click and see what the population value is. So two things can happen here, and I like to use the criminal justice system as the example. Last year when we had to switch to remote in March, I had just before we went on remote learning seen the movie Just Mercy with Michael B. Jordan, based on a true story, an extremely powerful story about our criminal justice system and these type 1 errors, right? When an innocent person is convicted, particularly with the consequence of a death penalty, which is what that movie centers around. So I highly recommend it. If we can, we'll watch it in class, maybe after we review for the AP exam. Really great movie and a really great example of type 1 and type 2 errors if we apply it to what we're looking at here. So if the null hypothesis is true, if the shooter is actually 80%, and we conclude that he's not, that's a type 1 error. If the defendant is actually innocent, and we conclude that he or she is guilty, that's a type 1 error. It's the most egregious. The probability of this is alpha, okay? The consequence in this context would be that maybe the player has to practice more, or we believe he's not an 80% shooter, and he is, right? So we conclude that this player makes less than 80%, but the truth is he actually is an 80% shooter, okay? No consequence to a correct decision, right? We decided, and this is what we did here, right? We rejected the null hypothesis, we peeked behind the curtain, which we can never do in real life, and found that we were correct. Here's the other way around, right? Correct decision, right? The null hypothesis is true, the defendant is innocent, and we reject it. So I was on a murder trial in Camden a few years ago, and it was a really great experience. It's funny how you sit in these jury rooms and most people are lamenting, I don't want to do this, I'm going to pick for jury duty. I highly recommend jury duty if you get the chance to do it, and I was in a situation where I was able to and make it work. It's a really good experience, and it's our civic duty, but it was a really interesting case. But at the end, after the prosecution presented their case, I was not able to change my mind on the null hypothesis that this particular defendant was innocent. There was not enough evidence to provide that this defendant was guilty. So with about 35 minutes of deliberation, we came back with a not guilty verdict. Was it the correct decision? I don't know. Right? We don't know. We made the best decision we could based on our assumption of innocence and based on the evidence that was presented. And that's what we do as statisticians. Okay? We make the best decisions we can. We don't know if it's not factual. It's not like geometry where we're proving anything. So when you make a conclusion in a significance test, you want to avoid language of like, we proved that the null hypothesis was false. We just have evidence. We're going to say we reject the null hypothesis because we have significant evidence that it's not true. Or we don't reject the null hypothesis because we don't have significant evidence to contradict it. So the type 2 error, so the consequences here is maybe this player needs to practice more. Maybe he's not an 80% free throw shooter. Maybe he lets his team down or his coach down when they expect him to make 80%, and he's actually not able to do that. In our criminal justice system, this is where a person who's guilty of the crime they were accused of is found innocent incorrectly. Again, the less egregious of the two. So, what I want you to do now is jump on our website applet and run through this trial one time, answer those questions, and then use the Quiz Me button up here at the top. I want you to click on that Quiz Me button and answer those questions.